So hi, I'm Darrell. I'm a senior data scientist at Kabamo. We build beautiful cloud-based software. I've been a data scientist for more than 10 years. I've been mostly working in the finance industry. I've done consumer lending, business lending, insurance. I've built all sorts of random models. I mean, there's been short text categorization, credit scorecards, image search. I've been only programming in Go for about 3 years. Mostly, I still do most of my work in R and Python and SQL. Okay, today we're going to go through these three things. What is deep learning? How to build a model in Gogonia, which is currently the only real way to build deep learning models in Go. And then after that, most importantly, how do you continue to learn and from all the examples that you can find on the internet. So first things first, what is deep learning? So deep learning is a subset of sort of a machine learning algorithm. It's a form of artificial neural networks, and we call it deep because the tendency is it has many layers, like an onion. And honestly, the way deep learning is being used now sometimes drives us a little bit mad. So, so then we're going to get to when should you use deep learning. So you should only really use deep learning when you have large amounts of examples. You should also only use it if your model can be a black box. That's to say, you don't have to explain exactly what it is your model is doing, and you don't necessarily explain all the peculiar behavior that tends to come out of it. Deep learning models also tend to be expensive, so you're going to make sure you have the budget for collecting all the data that you intend to feed into your model, train your model, and then after that, that's just the actual execution and inference of the model itself, which can be expensive, especially when you start getting into into the land of GPUs. The fourth reason you may want to use it is if you believe it can extract features that you can't extract normally otherwise. And of course, there is another reason, which is you may just want to have an emotionless machine make all your decisions, and yeah. So, how large are we talking about? Most of the time when somebody comes to me with a machine learning problem, they have hundreds of thousands of examples. When you come to deep learning, you want tens of thousands, hundreds of thousands, and ideally they're labeled unless you're going with reinforcement learning. And then for it to really, really shine, you want millions, even up into the billions of records. But really, it depends on your exact application. There are ways you can short-circuit this. You can use a pre-trained model, of which there are plenty nowadays. And I think the most important thing to remember is that deep learning is really only part of your solution. It's not going to be your entire solution. It's not going to magically solve all your problems. You still have to change your process around it. You still need to train people around how your model behaves, what to do when it does misbehave, and then how to audit sort of the behavior and make sure that everything is going according to plan. Let's see. So let's get into building our first model. So we're going to be using Gogonia because there's really no other choice, and Gogonia is great anyway. Before we build the model, we need to define our problem. So we need to define we need to define a problem. We need to find suitable data that we can train to help solve this problem. And then we also need to define a measure of success for our model. Because otherwise, how do you know whether you've done well or not? So the problem is, I'm going to go with the classic example, which is recognizing handwritten digits. So we're going to be using the MNIST dataset. So the MNIST dataset is a fully labeled and already separated dataset. There's already a train set, a test set. You don't have to worry about munging all of that. It happens to consist of handwritten digits that are 28 pixels tall by 28 pixels wide. Yeah. So for success, let's try and hit above 90%. So what does our model look like? So our model is going to take in 784 values. So if you recall, I mentioned it's going to be 28 pixels by 28 pixels. That happens to be 784. We're going to feed it into two hidden layers, the first of which has 250 units, and the second of which has 100 units, and then we need to output 10 values. The main reason we're outputting 10 values is because there are only 10 possible digits in MNIST, and we are going to one-hot encode it. So what is a hidden layer? So a layer typically refers to actually, it's a little bit misleading because it actually refers to a set of nodes within the model. So typically it'll contain a set of weights and then a bias term. And then after that, what is it? So yeah, so it looks a little bit like that. Y equals Wx plus B, which you may recognize from as a linear equation. So after that, it will usually end in the activation function. Usually this function is not entirely linear, so that your resulting model is nonlinear. So in this example, we'll be using the ReLU rectified linear unit activation function, which looks a little bit like this. So it will be a value, and for those of us who prefer if then else statements, there's this. So it will produce 0 if the input is less or equal to 0, and it produce the value itself if it's more than 0. And then for the output, we are going to be converting our labels to be one-hot encoded. We'll be using softmax to adjust the output of our network at the end. So softmax tends to just, so softmax, if you're not familiar with it, it just adjusts all the numbers to sum to 1. So it looks a little bit more like probability distribution. Our model itself doesn't care and will just produce any numbers it likes. So going on to the implementation. So you'll see, if you recall, we started with 784 values. So you'll need so in general, our first layer will tend to look like this. The first weights will have a matrix of 784 by 250. We're going to initialize it using the normal distribution, which is represented by this Glora n over here. Ooh, that works. Okay. Which is represented by this Glora n over here. So our declaration here just specifies a new matrix where G is the graph that we are drawing onto. DT is the data type. In this case, we're using float 64. With shape, so our matrix is 784 by 250. What is it? And it's called W1 because it's the weight for the first layer. Yeah. And then after that, you can see below that, we've also defined the bias. So the bias is here, B1 is defined similarly. You can see it's shaped 1 by 250. It has a name of B1, and it's also initialized with a normal random distribution. So let's see. So the second layer, whoops. Okay, second layer looks pretty much the same. But you can see we've changed the shape a little bit. Now it goes from 250 to 100, and the biases are 100. And then, let's see. Okay, and then for the last one, you can see we've gone from 100 to 10, which is our output, and then the biases of 10. Okay, before we get into exactly the exact node definitions, let's get into how we're actually going to implement some of this more visually. So when we are going to feed it, we're actually going to feed the data to it in batches. So we're going to actually make a matrix that's 100 by 784, so containing 100 of those images. And then if you recall, we defined our first set of weights, 784 by 250, and this should at the end give us a matrix of 100 and 250. So the keen eye among you may already notice that that kind of doesn't match our bias. So what we need to do then is actually to multiply it with a sort of a vertical vector of 1s to our bias vector, so that we can get another matrix that's 100 by 250. So that way we can add the two together to get a matrix of 100 by 250. So going into the actual code. So the code will look like this. So layer 0, we're going to set as our input. So our input, if you recall, is a matrix of, let's say, 100 by 784. And then after that, we're going to get into the actual math, so to speak. So you can see that in that on line 3, we are multiplying our inputs with our weights. We're also, then after that, on line 4, you can see that we're multiplying our matrix of 1s, which I've just called M1s. With our biases to get the correct shape. We're going to add them together, and then we're going to pass it through Rectify. So Rectify is Gorgonia's function for the rectified linear unit. And that's it for layer 1. So layer 2 looks the same. You'll see that it just has, it looks exactly the same. Layer 3 is a little bit different. So you see that instead of using Rectified, we use softmax, since this is going out into our output, and will produce all the numbers that we need to tell to see what is predicted. And then after that, we've said that our output is going to be layer 3. So there's one more important thing I haven't mentioned about what we need during the model. So we also need a loss function. So in the case of, So in the case of this example, we're going to be using something called cross entropy loss. I'm not going to get into the greater detail as to what it is, but in general, it is generally the mean is going to be is going to take a mean out of what's the word? Out of the multiplication between the actual value and the log of the predicted value. So our implementation in GopherConAU looks a little bit like this. So you see we've stacked together the log of our output, and after that you'll see something that I haven't mentioned before. So there's a Hadamard product, also known as, I think, the short product or dot product, where we're multiplying the two. Where essentially we have, because our output is going to be It's going to be a matrix of. It's a matrix of 100 by 10. So we're just gonna make sure that we're multiplying it. Rather than multiplying it, what's the word? Pointwise. Huh? You'll multiply it pointwise. Yeah, pointwise. We're going to multiply it pointwise instead of across. And then we're taking the mean, and then we're going to add a negative on top. There's a few more administrative details. I'm not going to get into too much detail about that, but we're going to use a new take machine. You may want to use another machine for when you want to build LSTMs, for example. I think that's called the list machine. And then after that, we're going to specify a solver. So in this case, we're going to use the RMS prop solver. Another solver that's very popular is probably the Adam optimization solver. And then we're going to tell you what batch size is. So in this case, our batch size is 100. And then this is the part where I thought I was going to go do a live demo, but then I realized it would take an hour to run. So I've prepared some. So here's some I prepared earlier. So here's a set of 4s that it got classified correctly. As you can see, they all look like 4s, thankfully. Here are the ones they got wrong. And the ones they got wrong tend to be more like, you can see there is sort of the shape of a 4. But it obviously likes a certain specific shape that sort of looks a little bit like a 4 that is taken as 4. So after all of that work, how accurate did we get? We got to 98.16 on this run at least. So 98.16 pretty much just means on the MNIST dataset that you've implemented it correctly. It's actually not difficult. It's actually not difficult to get to 98.16 on this test set. I believe the leading result on this is something like 99.79. So nearly nothing wrong, and probably better than most of us here if we were to do it ourselves. In real life, however, typically you're jumping for joy if you're above 70. And it's like if you're hitting 90 plus, it's like you're really just gonna take the rest of the year off, I think. Okay, so onwards. So typically most of the resources you're going to find online are from other popular libraries. So most of them are for Python. TensorFlow, Keras, PyTorch, Chainer, MXNet. Well, MXNet is not technically in Python, but it has Python bindings. The most popular of this historically has been TensorFlow. So TensorFlow is the most popular. It may become a little less popular now that it released 2.0 and broke a bunch of people's code. But yeah, and I think in the academia front, PyTorch has been picking up a little bit more steam. However, this is GopherCon. We write Go. So really, there's only one option, which is GopherConAU. There's going to be a second option soon, a little bit higher level, called Gogi. If you want to find out more about GopherConAU, you can go to gopherconau.org. Olivier has done a great job sort of refreshing the website. Sorry, it's not my website. But yeah. So Go isn't really, obviously Go at the moment isn't really the language of choice for deep learning. Not that we would let that stop us. learning resources are going to be scarce, so we just got to work with what we have. So let's look at a slightly more complicated example. So here, so we're going to look at autoencoders. It's got a few more layers. It's not that many more layers. So yeah, there are many, many examples on the internet for building autoencoders in TensorFlow, Keras, PyTorch. So I'm going to pick a few that look sort of similar-ish, and then we're going to try and port it into Gogonia. Well, I'm going to show you how to port it into Gogonia. Autoencoders, so the model, as you can see, is not that much more complicated. We've just added an additional hidden layer there, but you'll notice that the input and output notably are the same. They are 784. We're looking to produce as close as possible to the input in this case. In general, the first half of this tends to be considered the encoder, and the second half of this tends to be considered the decoder. And sort of like, I think sort of the notional idea is that you're teaching your model to find a way to encode or compress data from 784 values, for example, into the 50 units that we're given it. So in TensorFlow, this looks a little bit like this. So you'll see this is not too dissimilar from our Gogonia example earlier. It goes from 784 to 250, 250 to 50, 50 to 250, 250 to 784. Our biases are appropriate, 250, 50, 250, 784. It looks very different in Keras, if you try and do this in Keras. So in Keras, the declaration tends to also include the activation functions. So you'll see we only declare the units in this case. 784, 250, 50, 250, 784. You also see the activation functions there at the end, relu, and sigmoid. And then in PyTorch, again, the declaration is a little bit more similar to TensorFlow and Gogonia. You see the matrices, 784, 250, and so on and so forth. So in Gogonia, you've already seen this. I don't have to show you this again. It looks pretty much exactly the same. So in TensorFlow, the declaration is also extremely similar to Gogonia. Relu is just called relu. You can see the addition, you can see the matrix multiplication, and you can see the biases. So these are the first two layers, the encoder layers. And then you'll see on layer 3 and layer 4. So you can see layer 4 is a little bit different. It has a sigmoid at the end. Yeah, it has a sigmoid at the end. And then for Keras, you've already seen it. It looks pretty much the same because we've already declared the structure and the activation functions at the end. Let's see what's next. Yep, and then in PyTorch, usually you put this into a forward function in your autoencoder object. So you do pretty much the same thing. You're gonna stack it over relu, sigmoid, and then return the value. Let's see. And then in Gogonia, you've seen this already. So rectify, add, multiply by the weight, multiply to make the bias the right shape, and so on and so forth. So layer 1, layer 2. What is next? Layer 3, layer 4, and then you can see the sigmoids at the end. So it's a little bit different. Okay, so a little bit of a sneak peek with Gogi. It's not out yet. So you can see here so it looks a little bit more similar to Keras. You only need to declare the units. You don't have to declare every single matrix one by one. And so you'll see there's a G. So G here is short form for Gogi, and GG here is short form for Gogonia. For anyone following. So here's where we go. Yeah. So you can see the declaration involves our activation function at the end. Whoops, wrong button. Activation function at the end. So rectify, and sigmoid. And then you can see all the units going straight up and straight down. Then after that, the most important part is the loss function, which is in TensorFlow. It's not too complicated. You can see it takes the true values, subtracts the predicted value, takes the square of it, and then reduces it to a mean. In Keras, you declare it in the compile in the compile call, here's also where you tend to put the optimizer. So if you're looking at a model and looking for the optimizer, look for the compile in Keras. So you see it just says loss mean squared error. And then for PyTorch, you see it just says nn.mse loss. So what the heck is mean squared error? Oops. What is mean squared error? So usually if you Google, you're going to get a formula something like this. So again, y minus y hat is your predicted value. You're going to square it and then take a mean. So in Gorgonia, this looks a little bit like, so this looks a little bit like this. So you can see there's the subtractions between the y and the expected value. We take the square of it, and then we take the mean, and that gives us our loss function. Okay, so again, if we were to run this, it would take another couple hours. Going on to the results. So you can see, I'm not sure how clear. Yeah, it's pretty clear. That's great. So you can see on the left is our inputs, and on the right is on our outputs. So you can see it's a little bit blurrer, a little bit noisier. There's definitely nothing we can't fix. Yeah, definitely nothing we can't fix. But that's the results. What else? Oh, that's it. That's it. Yeah. So just a little bit of a plug. I'm CFGD on Twitter. I've written a book entirely on this topic, so please buy it. And if you need cloud-based software build, please come speak to us at Kablamo. We also have a booth outside. Yeah, thanks.